Have you ever looked at an electric vehicle and wondered what the future of car engineering might really look like? Not just batteries and quiet motors, but something radically different. Something that doesn't just change how cars move, but how they react, corner, accelerate, and even think. Well, today you're about to discover one of the most revolutionary ideas in modern automotive design: in-wheel motor technology, a system that removes the traditional engine entirely and places power directly inside the wheels. Sounds futuristic, right? Let's break it down and uncover why major automakers are exploring this technology, what makes it so promising, and the surprising challenges that come with it. At its core, the concept is beautifully simple. In a traditional gas-powered vehicle, power has to travel through a long chain of mechanical components: the engine, transmission, clutch, driveshaft, and differential. But an in-wheel motor throws all of that out the window. Instead of a central engine, each wheel can have its own electric motor mounted inside the hub. This means the wheel itself becomes the power source. No driveshaft, no gearbox, no transmission losses, just pure electric torque delivered directly to the road. And yet, despite being simple in theory, this tech raises important questions. How durable can it be? How powerful? How efficient? How safe? Let's dive deeper. Mounting the motors inside the wheels frees up enormous space in the rest of the vehicle. With no bulky engine bay, automakers can rethink cabin layout, battery placement, aerodynamics, and weight distribution. But for every benefit, there's a new challenge. In-wheel motors face harsh realities. They're exposed to dust, water, mud, salt, rocks, vibrations, and constant shocks, all of which can shorten lifespan. This is one reason some early experiments, including certain truck prototypes, abandoned the concept. Still, the potential advantages are too big to ignore. Here's a fun twist. In-wheel motors aren't new. Back in the early 1900s, Ferdinand Porsche built a hybrid vehicle with electric hub motors on each wheel, one of the earliest examples of a multi-motor drivetrain. Those early motors directly drove the wheels without a gearbox, meaning the wheel speed was exactly the motor speed. That sounds efficient, but it means the motor must create enough torque on its own, since there's no reduction gear to multiply it. Modern technology, however, has made direct drive motors far more capable than those early experiments. You might be surprised. When multiple in-wheel motors are combined, the system can exceed 600+ horsepower. And because electric motors deliver torque instantly, the response is nearly immediate. But here's where it gets even more interesting. Every wheel can have its own set of sensors that constantly monitor grip, speed, and traction. The system can then precisely calculate how much torque each wheel needs at any moment. Instead of a central engine guessing how to distribute power, each wheel becomes a self-contained powerhouse. This leads us to one of the most exciting aspects of multi-motor EVs. If you've ever heard the term torque vectoring, here's the simplest way to understand it. It's the ability to send different amounts of torque to different wheels to improve handling, cornering, grip, and stability. Traditionally, torque vectoring is achieved using mechanical differentials or brake-based systems that slow certain wheels to help the car turn. The downside? Those methods waste power and aren't always precise. But when each wheel has its own electric motor, you unlock true torque vectoring. No wasted energy, no delay, no mechanical losses, and instant response. That's why electric vehicles with independent motors can corner like sports cars even if they're heavy SUVs or trucks. Let's compare three setups. Internal combustion vehicles require engines, transmissions, exhaust systems, drive shafts, and differentials. Lots of moving parts means lots of mechanical losses. Regular EVs replace the engine with a central electric motor, inverter, and battery pack. Better, but still dependent on gears and shafts. In-wheel motor EVs remove everything and place power directly in the wheels. The only major mechanical component that remains is the suspension. The result is fewer parts, less weight, more control, greater efficiency, and instant torque. And because the motors are independently controlled, torque vectoring becomes effortlessly integrated. This is where things get complicated. Yes, in-wheel motors eliminate gearbox losses, but they can't be decoupled from the wheels. That means they always spin and always experience no load losses. Traditional EVs sometimes decouple rear motors at cruising speeds to improve efficiency, something that's very difficult with in-wheel motors. Still, some companies argue that the direct drive design reduces energy loss overall, especially in city driving. And regenerative braking works wonderfully here, giving back some energy every time the vehicle slows down. In stop-and-go environments, in-wheel systems can achieve around 90% efficiency, compared to around 20% efficiency for internal combustion engines. Several companies are actively testing or developing in-wheel motor technology. Porsche Engineering is working on a 4-motor torque control system that gives SUVs sports car-like agility. Nidec in Japan is developing compact, quieter motors. Venturi is experimenting with high-performance concept vehicles. These systems aren't theoretical. They're being used, refined, and tested right now. One of the most dramatic demonstrations of multi-motor power is seen in modern electric trucks. Take Rivian's quad-motor system. 1 motor per wheel, around 800 horsepower, 0 to 60 miles per hour in 3 seconds. And independent torque control that allows the truck to behave like a sports sedan on pavement while dominating off-road terrain with unbelievable precision. It's not the cheapest truck in the world, but it's certainly one of the most capable. There are many reasons automakers are excited. In-wheel motors are compact, flexible, highly efficient, and extremely precise. They eliminate mechanical losses, reduce drivetrain components, expand interior space, improve weight distribution, and deliver instant torque exactly where it's needed. But the downsides are equally important. They increase unsprung weight, which can affect ride quality. They endure constant shocks from potholes, bumps, and rough roads. They are exposed to dirt, mud, water, and salt. They cost more to produce and require more complex maintenance. And long-term durability is still uncertain. The truth is, the technology is incredibly promising. The potential for razor-sharp control, unmatched traction, and simplified drivetrain design is massive. As electronics, materials, and motor efficiency continue to evolve, the limitations of today may disappear tomorrow. We may soon see electric vehicles capable of moving sideways, rotating in place, climbing obstacles with extreme precision, or navigating tight spaces with movements that traditional cars simply can't perform. In-wheel motors might not be perfect yet, but they are shaping a future where vehicles become smarter, more agile, and more efficient than ever before. What do you think? Are in-wheel motors the next step in electric vehicle evolution? Is the world ready for this level of control and innovation? Let me know your thoughts.